Hello everyone. This video is about prime numbers. Specifically, it is about prime numbers and their endings, which after the number 10, they become 1, 3, 7, and 9, and their relationship within a matrix of the known prime numbers up to around 100,000. Now, I decided to do a little experiment and extend the ending of prime numbers, since prime numbers up to 20 are 11, 13, 17, and 19. So I decided to include them and convert the prime numbers into base 20 and find out the relationship of prime numbers with the endings of 1, 3, 7, 9, and 11, 13, 17, and 19. And these are symbolized, like because of base 20, it needs a single digit on the end. And since you run out of digits, single digits, you have to start using letters or other characters. In this case, the characters are simply letters. A being 10, B being 11, C 12, and D 13. So naturally, the four prime numbers from 10 to 20 are 11, 13, 17, and 19. And they are represented by B, D, H, and J. And so what I did was that I took these numbers and from a stretch from 20 to 40, and from 40 to 60, and 60 to 80, and so on, all the way down to the last prime number. And I populated them with the prime numbers. So here you can see 20 and 3 is 23. 20 and 9 is 29, and 20 and B, which is 11, would be 31, and 20 plus H is 37. And the same with 40, and then the 40s come, and then you got 41, 43, 47, 53, and 59. So as you're going along, you collect up all these various configurations of primes in stretches of a 20-digit stretch, and so you end up with a kind of a matrix here of numbers, and you see two columns here. One is for primes to nearly 50,000, and the next set of primes here is primes to nearly 100,000. So I didn't go quite to 100,000. There's a total of 99,991 primes in this. But I felt it was enough of a population to do my experiment, and I found some very interesting things. When you take a look at the distribution of the primes using the last digit and the combinations thereof from 20 to 40, say, like 20 to 40, you get 39BH in because you get 39BH, so that's one combination. So what I did was that there's a total of 256 combinations of prime numbers in this set. There's 256 total. So I decided to take all these combinations and decided to count them. And so here's this first column. These first three columns here after the concatenation of these digits. It gives me the number of blanks, the number of times 1 shows up, the number of times 7 shows up, the number of times 9 shows up. And on the other column, it's just as a check, just to see if I've got the right number of primes totaled. This is the total number of primes, like 1 and 3 would be doubled, so it'd be 275, you see 550 here. So after totaling all these up and getting all 991,000, I got all the combinations, which is, as I say, is 256 numbers, and I decided to count these combinations. And I found something very strange. Some of the combinations, when you get to at 137, you get 183 instances. 139 has 178, but 13B has 0, and as does 13H. So that means, what this means is that 1, 3, and 11 do not show up in any combination of primes from a set number of 20 to in a set of 20. And there's a number of these 3 digits, like 13H, which is 1, 3, and 17, and 1, 9, 11 doesn't have any. 1, 9, 17 doesn't have any. 3, 7, and 11 don't have any, and 3, 7, 17 don't have any, and 3, 11, and 13 have none, as does 3, 11, 19, and so on. And there's a few of these holes that are absolutely empty. Now, obviously, I want to point out that these numbers are only up to 100,000. I mean, there's no proof that there couldn't be a 1, like after a million tries, that maybe something will come in. But I guess well, what we got here is a kind of conjecture here, that I'm kind of making a conjecture that these holes, no matter how high you go, you will never populate these combinations of primes. These primes will never have combinations. So I don't know what I've looked up on the internet. I don't know what this conjecture is called. For the sake of brevity, and because I don't know what this is, I'll just call it the Teddy conjecture. So anyways, this Teddy conjecture is something that I don't know how to really sort out. However, I want to point out that this has nothing. These zeros have nothing to do with the Riemann hypothesis. Well, at least I don't think. Maybe tangentially or in a nebulous way, perhaps, but it's not, strictly speaking, anything to do with the Riemann hypothesis proper. So just wanted to make sure that I'm not misunderstood here. I'm not trying to say that these are Riemann zeros or anything to do with Riemann zeros. Although in the sense of their character, maybe there's something there tangentially with Riemann, but strictly speaking, they have nothing to do with the Riemann hypothesis proper. Until, well, they might have, but not in a straight linear way. So one thing I notice about this is what I've done here is that, I mean, this is kind of like and my further experiments will probably try to bear this out. And because there's still, even though I've done this, there's still really no set pattern of these primes to 20 done in the way that I have done it. But there is something. Well, I'm gonna have to brush up on linear algebra, because this is kind of I don't know whether you can matrix or make vectors out of these, because whenever I see zeros here or something like that, it kind of means that there's because these zeros actually are the vectors obviously coalesce to a zero for some reason, which I don't understand. But this matrix can be somehow used to figure it out. Now, I'm not sure whether linear algebra has the necessary tools to make a proper plane of these primes that are missing, and whether or not why these holes exist and why these primes don't like living together in a set of 20. I mean, because like a lot of other ones do. And of course, naturally, as you go higher and higher in primes, these differences become more and more sparse. But you can see that as you go down, there's other anomalies in here too that are kind of strange. Like, for instance, there's one, the deepest as you go is like 6 primes in one, but it occurs 8 times. And here's one where it occurs 6 times. So 14 times you've got 6 digits within 20. And here you have 5 with 13, and of course, naturally, there's 5 with 18 and so on. But those aren't the ones I'm so concerned about. The ones I'm concerned about are the ones that are I guess easier to have a population in, like 13B and 13H. You'd think that they could at least have a few. I mean, they vary in their populations quite starkly. Like, for instance, like BH occurs like quite a lot, and 39 occurs quite a lot too, like in combinations of 2. So I would like to know which primes happen with this. And so I've got to do a little bit more research. So thanks for watching, and if you're interested, leave a message in the comments. Tell me what you think, and if you know anything about this experiment, or if it's been done again, or if you can correct me on like the Teddy conjecture, if there's a proper name for this conjecture, let me know what it is. Anyways, thanks for watching, and I'll get back to you soon when I play around with it next time and see what comes up when I start experimenting a little bit more. Take care.